So in a few of the previous problems, you kind of do the same derivation over and over again, where you have the centripetal force on these particles equaling the mass times the centripetal acceleration. The centripetal force is provided by the magnetic force, which has a formula of Q V B times sine of theta, but that's sine of 90 degrees because they're perpendicular, equals m, and then v squared over r for the centripetal acceleration. And you have this v on the left canceling it with one of the v's on the right. So you kind of end up with this final expression here. I'm just going to be a little lazy here and not write magnitude bars and just write it like this. Okay, and that formula showed up a few times already. So we answer questions like these ones, part A. If the magnetic field strength doubles, how will that change the radius? So it's really trying to highlight how these variables are related to each other. So when I look at this equation, and I look for B and R because magnetic field strength is B and radius is R. So look at how B and R are related. I would see they're on opposite sides of the equal sign. And B is in the numerator and R is in the denominator. So what I see immediately is that B and R are what we say inversely proportional to each other. So if one of them goes up, the other one goes down by a reciprocal factor. So therefore, if B doubles, then the radius will halve. If you're not comfortable with just looking at the equation and identifying that they're inversely proportional, what you can do is rearrange it for r. The question asks how will it change the radius, so you can rearrange the equation for r, which will look like this. It'll look like mv over qb. And then maybe you can see that a bit easier, that if I were to double this b value in the denominator, that would cause my r value to be cut in half. B. So for B, they want to compare the speed with the radius. So similar kind of question, the speed and the radius. So when I look at the equation, I'll call this equation star, the V and the R are on the same side of the equation. One's in the numerator, one's in the denominator. So if I double one of them, the other one has to double as well to keep the equation the same. The left side of the equation, Q times B. We didn't change any of those things, so if that's got to stay the same number, then doubling the V means I have to double the R. So I'll say that since QB is not changing, if V doubles, R must double to keep QB constant. I guess there's also the mass there, but we assume the mass of the particle is not changing either. Yeah, so that's just analyzing equation star. I could actually analyze the other equation I have written on the right there. Similarly, let me give that a name. We'll call this equation, obviously we'll call it equation double star. So if I look at equation double star, R equals, and I doubled my V value. If that doubles, then my R value is going to double. Whatever I calculate, it's going to be twice as much as well. So R and V are actually directly proportional. C is a bit more interesting. If the kinetic energy of the particle is doubled, how will that change the radius? We have to actually make an assumption here, actually. How do we double the kinetic energy? Probably by making it go faster. But how much faster? So remember, K equals half mv squared, or V equals root 2k over m. So if I double the kinetic energy, I actually increase the speed by a factor of root 2. So doubling k increases v by a factor of root 2. This in turn increases the radius by the factor of root 2. We saw that from part B, that if you change V, then you change R by the same factor. So that one was tricky. It involved 2 steps there. And D, if a particle of equal mass but double the charge is used, what else will need to be adjusted if we want to keep the same radius? Okay, so we're going to change the particle out. We're going to change the particle to one that has the same mass, but it's got double the charge somehow. Maybe it's got an extra proton and one less neutron or something like that, in order to keep the same mass but double up the charge. If we want to keep the radius the same, how can we do that? Okay, well, there's a couple of ways. So if I analyze equation star, if I double this Q value, double the charge value, but I want my radius to stay the same, well, one thing I could do is I can cut the magnetic field strength in half, and that'll balance out the differences. Okay, so if I've doubled the charge but the same mass, I could try to cut B in half to keep my same radius. Similarly, maybe I'll look at equation double star. That might be easier actually, because it's been isolated for the radius. So if I've doubled my Q value, keep the mass the same, what if I keep the B value the same? I keep my magnetic field strength the same. Well, then I could also change maybe the speed that I fire these particles in at. So if I double the Q, I could also double the speed, keep that ratio the same. That'll keep the radius the same as well. So there's 2 options. Also some kind of combination of the 2 would also work, but I won't do that. So we could have the magnetic field strength or we could, keyword is or. We can't do both at the same time. That'll change up the ratios. We could double the speed. All right, so that's just trying to understand how variables relate to each other in this kind of an equation.